If you have a long electrical cable, the reactance may be high. If you have a short one, the reactance may be long. So this is clear. Okay?
Yeah.
Length is the most important if you want to have a big.
Yeah.
And most of the reactance is sitting in the flexible cables, if they are 10 meters long. If you have this, and you have this, then the reactance here, and here, high or low? High or low?
Low. High.
This?
This high?
Okay. Is this very good? No. If you have the current loop is a low and with a high distance. The reactance here is high or low?
High. Low.
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 The bigger the distance,
Yes, this is.
the higher the reactance. The larger the reactance. This must be higher and this must be low. If the distance is very small, the reactance may be low. Is that correct? Yeah? Okay, I do not know if there's a mistake. I will ask Mr. Adas. And if you have this system, phase A, B, C, this is what we speak today very often. XA is identical to XC, but greater than XB. This is low. This is a big problem of all constructions. And you know, there is, you can calculate this difference between XA minus XB. Divided through the length. I have calculated this some years ago.
저기서 컨덕터의 길이지.
Oh ja. Delta X is frequency permeability mal ln4. And this is 87,1 Mikroohm per Meter. Right. If you have this system, there's a difference between the outside and the middle phase, And this is given by this formula, if this is a long distance. And you can calculate this is 87 micro-ohm per meter.
It doesn't work.
Ja, sind Sie schon ausgeschrieben?
Weiß ich nicht.
Okay. Well, this is very important for us. If you have an 8 meter long electrode arm, this is 0.6 milliohm reactance difference. Now we will write it as 8 meter, 8 by 8, the difference delta x 9,6 milliohms. Solange die Elektrodarm ist, ich habe mal ausgerechnet, wie groß die Differenz ist, wenn wir ein paralleles System haben. Das ist given by this formula. And this formula is independent from the distance. If you have a big distance, the same formula. And this is a problem of design we have. And we have different ideas to get symmetrical reactance. This is very important. We will speak what is the reason for this. Why do we need symmetrical reactances in each phase? And what constructions we have to do that. This will be a big time for me to speak with you. Okay? First I will speak to you about this formula here.
Yes.
How you can get this formula. I will calculate this on the yellow paper like Professor Ahlers. Es geht. Und ich weiß, warum es bei mir nicht geht, weil ich okay nicht gemacht habe.
Das passiert bei mir auch immer wieder.
Ja?
Gerade auch beim Hotel im Internet anmelden, da muss man auch OK drücken öfters.
Well, first, we will use the equivalent circuit of an electric arc furnace. I will tell this one. This is X, and this is the distance. This may have the loss resistance and the arc resistance. And this is phase 2. And 3. Okay. We have a symmetrical supply network with 3 symmetrical voltages face to face. And we can show that these voltages are equal, the face-to-face voltages from the transformer. You can have this paper when we This is the first face-to-face voltage. This is the second And this is the third, yeah? 1, 2, 3. We understand this is a symmetrical network. Equal voltages, phase angle is 120 degrees. And now we say first, we have a symmetric system. All x are equal and all are equal, yeah? Then we can calculate this formula there. Then we need information about the star point. The star point is free. Yeah? It's free. And you know this is the potential of the bath. And if you have the furnace, this is the bath. Bath nearly Earth. Okay. And if we have a symmetrical system, 3 equal resistance and reactances, then this potential is in the middle of this triangle. In the middle. And these voltages, the currents, are equal the power in each arc is equal, and we have 3 identical powers, and the sum of the power is the total power. We can also say the phase voltage from 1 to 0 is this phase voltage. Yeah? And the phase voltage from 2 to 0 is this voltage. And this is the third. Okay? Now we can calculate all voltages are equal, all currents are equal, all powers are equal. And we can say now the total power, active power, ja, ist klar. P is 3 times.
Hallo.
Hallo.
Hallo?
Zu trinken?
Ja? One coffee? One coffee?
Kaffee?
3
Coffee?
coffee.
Okay.
3-mal.
Dreimal. Und Wasser
Es geht-
auch wieder? Oder?
Wasser, nein.
Nur 3.
Das geht auf meine Rechnung, Tim.
Okay, weiß ich Bescheid. Dankeschön.
Ja, danke schön.
Bring ich gleich hoch.
Ja, ist gut. We talk 3 phases, and the power here is the square of multiplied. Is this clear?
Yes.
Okay. 3 equal phases.
Yeah.
And now we must calculate the current. The current is voltage divided through the impedance. Yeah? E is the phase voltage, I would say phase, divided through the impedance. The impedance is square root of x quadrat plus r quadrat. Okay, is that good?
Yeah.
And you can see, most you know this voltage. This is a step face-to-face voltage, which is given by a transformer. You know this. Most say, ooh. Yeah? And you know, now must calculate how is this in behalf of this. This, the phase voltage is smaller than the face-to-face voltage.
Yeah.
What is the difference? The square divided 2. This is square root of 3 is smaller.
Yeah.
And now E divided to P. And we put this in this formula, yeah? P 3 E quadrat. U quadrat divided to 3 is this. And this I okay, quadrat, doch Widerstand, yeah. And now, I will think what to do. I forgot this, yeah. And now, I'm writing yeah. Two x here and 2x there. This is allowed. Yeah?
Yeah.
And then can you see this is the impedance, this is the reactance, and this is the resistance, and this is the phase angle phi. You see that this divided through this is the cosinus phi. Yeah? And this divided to this is sinus phi. And now here stands 2 sinus phi cosinus phi, and this we can find together. This is sinus 2 phi. And this 3 is, you can forget, and therefore we see P is the square root of the square of the phase-to-phase voltage divided to 2x multiplied with sinus square. This is the formula. Yeah? You can have this later, the symmetrical system. This formula shows we have the furnace power is dependent from the transformer voltage. Yeah? It's dependent from the reactance. It's dependent from the phase angle. This is given by the impedance component. This is the high current system. This is what we are speaking. 4 days. And this is a very important formula. And now I will speak to you together. What can you do to get most of the steam makers want to have a big power? What can you do to get a big power? What can you do with this formula? Can you do here something? What is this? What is the maximum? What is the maximum of sinus 2, 2 phi. How big can? What? One. Yeah, you see the one? And the phase angle must be 45. Yeah, very good. If then single phi. Then we can say the maximum what you can get in the furnace is square of the voltage divided with 2x. Many people are working with this formula. And now you can say, what can you do with the control? You can only this, 45 degrees here. But what can you get here to get a big power? What can you do? Many years ago, this was not allowed to get more than 1,000 watts. It was a face-to-face one, because of the security of the people. Now it's allowed to go to 1,500 volt. This is a high voltage area, and if you have a high voltage area in Germany, only special people are allowed to go in the room. Must be a closed room, and therefore they have a special order for arc furnaces. I have worked on this to get the standardization. It took me 7 years to change the standardization. Yeah, we are laughing from 1,000 to 1,500. Ja, mach mal auf. And the other value is we can change this. What can we do? Make a high or we can low? Ja, okay. Finde ich aber ganz lieb und nett.
Wieder gerne. So, wenn irgendwas sein sollte, rufen Sie einfach eine Rezeption an.
Ja,
Dann kommt wieder
schön.
ne?
2020 ist die Nummer, ja?
Also wir haben viele Nummern. Müsste die sein, die am Telefon stehen.
Achso, okay.
Gut,
Ja, vielen Dank, Dankeschön. Kommt ihr heute Nachmittag nochmal?
Wenn Sie es möchten.
Ja, nachmittags nehmen wir auch gerne einen Kaffee.
Wann denn? Wieder um 3?
Ja, um 3?
Komm ich
Okay,
hoch,
das ist nett, danke. Okay. X low. What happens if you make this to a low value? What happens? You make low. Instead of 2 million, 1.5 million. The furnace power is increasing. You can do that, but there can happen something. There can happen that. You must think of the current. The current of the system, I'm writing here. This is S is the SQP. SQP. This is the active power. The reactive power. This is the the Scheinleistung in Germany.
Surface power.
Yeah. How do you call it?
Surface power.
This is not a physical value. It's only Yes? Yeah? Okay.
Yeah.
You see? The smaller the higher the current. The smaller the reactance, the higher the current of the system. And therefore, we can construct electric arc furnace with very small reactance, but you get very big short circuit currents. And these give very big forces on electrodes. And the electrode began to vibrate, and the forces can be so high that your system, the electrodes are breaking from the short circuit current. And therefore, no, it's not good. Because current is going high, yes? Okay. Is that correct?
Yeah.
Okay, now we would like to make a coffee break. Okay. Do you have any questions?